We have now finished the fourth and fifth phases of the telescope alignment. We call those phases coarse phasing and fine phasing. And that's where we've made the primary mirror, all 18 mirror segments, into a single primary mirror. And we've initially aligned the telescope to the NIRCam instrument. That's the instrument that we use to do the alignment. And we've taken our first images. In fact, the team gathered over the weekend when the first images came down. We were in the Mission Control Center, and it was a very emotional moment. We kind of blew some of the image of stars up and really could see how it was performing. And I'm happy to say that the optical performance of the telescope is absolutely phenomenal. It is really working extremely well. And we said last fall that we would know that the telescope is working properly when we have an image of a star that looks like a star. And now we have that, and you're seeing that image. This is actually a 2100 second exposure taken at roughly 2 microns, which is the wavelength which Webb was designed to work at or above. And you not only see the star and the spikes from the diffraction of the star, but you see other stars in the field that are tightly focused, just like we expect, and all sorts of other interesting structure in the background. We've actually done very detailed analysis of the images we're getting, and so far what we're finding is that the performance is as good, if not better, than our most optimistic predictions.
The goal here was to build a telescope 100 times more powerful than anything we've had before. From the early engineering data that we have seen so far, we know that we're on track to meet those very demanding science requirements. The engineering images that we saw today are as sharp and as crisp as the images that Hubble can take, but are at a wavelength of light that is totally invisible to Hubble. So this is making the invisible universe snapping into very, very sharp focus.
Including the sun shield and the mirrors. The open sun shield helped cool down the instruments and mirror to about -400 degrees Fahrenheit. One of Webb's final deployments was releasing the mirror segments from their launch locks. Then we could start the mirror alignment process.
The images are focused together as finely as the laws of physics allow. This is as sharp an image as you can get from a telescope of this size. And as we were focusing the telescope, we were using typically one bright star at a time, a handful of different stars we used on the sky. But as we were focusing on those bright stars, we couldn't help but see the rest of the universe coming into focus behind them, to see the more distant stars and galaxies coming into view. And honestly, the team was giddy at times just seeing this happen. There's no way to look at these data and not be excited at the scientific possibilities that are opening up here.
And liftoff.
Décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. We're 13 minutes, 55 seconds into the flight. And there is the view from the upper stage camera on the Ariane 5 looking at the James Webb Space Telescope as it moves gently away from its launch vehicle.
Fantastic pictures of this telescope.
Go Webb, go Webb.
Screw up some of this input or
before like get noticed an hour before the contact.
A telescope is really a time machine. Because light travels at a finite speed through the universe, we see the universe as it existed when that light was emitted. It's traveled through time and space, and we detect it later on. For instance, if you want to have it in comparison, you look at the moon. It takes light about 1 second to travel from the moon to us. So we see the moon as it was 1 second ago.
the Earth is here. This is the Earth. And then we have the moon going around the Earth. And the obvious place we're going to put the telescope is orbiting around this one over here. James Webb Space Telescope is often called the successor to the Hubble telescope. But that's really slightly a misnomer because, first of all, the Hubble telescope's still operating and may operate for another 5 or 10 years if we're lucky. And secondly, it's a very different kind of telescope. The Hubble telescope is optimized to see the part of the universe that our eyes can see, whereas the James Webb telescope is optimized to see in the infrared part of the spectrum, which gives us a whole different set of information about the universe.